I think the final talk for today, I guess, is my own. So it's the talk about, can we blame the Linux kernel instead of OVS? Yeah, let's go ahead, roll it.
Instead of open vSwitch session at the OVS OVN Conference 2023. My name is Ilko Shadron, and let me walk you through the agenda of this session. We start off with the explanation of the problem, then we will introduce the kernel delay Pi tool, which its goal is to solve the problem, and then we demo the tool trying to debug a revalidator issue, and the remaining time will be left for questions. A lot of times when you're trying to debug the actual problem, it's not really clear if it's related to the kernel being overloaded or OVS, having a real issue. And the goal for this tool is to quickly determine one or the other so that you can focus your debugging efforts. Most of the time you start your debugging efforts with log messages like the following, like unreasonable long poll intervals or your thread being blocked for a number of milliseconds. And it's hard to determine if it's the kernel misbehaving or it's OVS vSwitch D. There are some specific tools out there that you could use, but they're not really coordinated, and it's an effort trying to figure out what tool to use at which time. So it will be better to have a single tool to rule them all. This is why I came up with the kernel delay Python tool that should be able to do all you need in a single place. I probably should have added a question mark at the end of the tool name, but this is not really delaying the kernel, it's just a tool to measure the delay introduced by the kernel. So kernel delay is a Python-based script. It uses eBPF hooks and programs to gather the statistics it needs. It does this based on the BCC framework. See the footnote below for more details. It can trigger on demand, meaning that if you start it, it will run for a certain period of time and gather the statistics. However, you can also use stop and start triggers. These are based on eBPF hooks, but we will discuss it a little bit more later on. Currently, it will capture 5 different types of statistics, but we will discuss that a little bit further down the road. There is also a blog post and user documentation available upstream. See the links below. This is what you will get if you start the application without any parameters. It will run for about 500 milliseconds, capture the statistics of the running OVS vSwitch D process, and then exits. There is nothing specific about this script to bind it to OVS. It can run with any applications. There is a --PID option where you can set the PID of the process you would like to capture data from, and then it will just run. So as mentioned before, the kernel delay has 2 modes of operation, either time mode, where the tool will run for a specific time and collects the information, or triggered mode, where the event collection can be started and or stopped based on a specific eBPF probe. We currently support the following set of probes, USDT probes, which are compiled in at compile time by the application itself. And then the kernel trace points, K probes, K return probe, user probes, and user return probe. The later two can be any function of the user space application that is actually available in the debug symbols. This might be useful when you're trying to debug specific functions. So how long does it take for this function to run, or why is this function taking an excessive amount of time? Additional sample options exist. For example, how many measurements you would like to take, or ignore specific measurements if they take less than a certain amount of time. Or if you would like to delay between 2 measurements. Start and stop triggers can be used in any combination, so you can have start only triggers, stop only triggers, or start and stop triggers. Let's take the start trigger here, for example. You can see it will start as soon as the bridge run function is called, and then it will sample for 4 seconds, and then does it 2 times with an interval of 1 second. The stop only trigger example here will start sampling immediately at start, and then it will stop sampling as soon as the bridge run function returns, with a sample count of 4, which means it will take 4 samples with an interval of 1 second. And then finally, the stop and start trigger example here. It will start when the bridge run function is called, and it will stop when the bridge run function is completed. And it will take 4 samples with an interval of 1 second. But those 4 samples are only captured if the trigger delta is more than 50 microseconds. So if the bridge run function does take less than 50 microseconds, it's not captured. This slide shows the available probes that can be used as stop and start triggers. The first one is the USDT probe, and then OVS has a preset of defined USDT probes. More information you can find in the user documentation referenced below. More details on the other probes you can find in the BCC documentation, also referenced below. As mentioned before, we currently support 5 statistics that are gathered, but the framework is built in such a way that new features can be added easily. The next slides will go over each individual statistic separately. The syscall statistics will record each syscall, and per syscall it will record the total calls, total duration, and the worst case duration. Note that it will only record syscalls that are started and completed during the measurement interval. Thread run statistics report how long the thread was running on a CPU. It counts the times the thread was scheduled on and off. It records the total minimum and maximum CPU time. It also only counts events that started and stopped during this interval. Thread ready statistics report how long the thread was waiting to be scheduled on a CPU. It records the total and maximum schedule delay. It only counts events that started and stopped during this interval. Hard IRQ statistics report the time spent servicing hardware interrupts during the thread's runtime. It records the per IRQ vector, the count, the total duration, and the worst case duration. Soft IRQ statistics report the time spent servicing soft interrupts during the thread runtime. It records per IRQ vector, the count, the total duration, and the worst case duration. The tool also has an option to record all syscall events. If desired, it can record syscall events which take longer than a specific time. It also shows a stack trace which can be disabled. And it has an option to not include poll system calls. So demo time. This setup has OVS with TC-Flower hardware upload, and we're using OVS perf to generate some traffic. If you look at the logs of this setup, they show a lot of unreasonable long poll interval messages for the revalidator threads. You see 1+ seconds, so we could use the tool to capture revalidation runs that take longer than 1 second. This is how we could do it. We use the USDT probes defined by OVS that mark the start and finish of a single revalidator run and apply them as triggers. We also tell the tool we want to capture the statistic if the run takes 1 second or more. Here we see that a single run already takes more than 500 milliseconds, so this might already be something to investigate. Here you see the single run time decreasing when the flows are being evicted, followed by a trigger for the first event that takes more than 1 second. So my OVS has quite some threads, so let's quickly scroll up to the first revalidator thread in my system. Here you can see that we spent about 1.1 second already in send messages. There are like 17,000 of these being sent. And you see that there are some worst case of taking almost 3 milliseconds. On average, it should be, 65 microseconds each, but so there are some ones that take a lot longer. And also the few tags seem to take quite some time, like 300 milliseconds in total. So yeah, that's quite a lot. And we should probably try to debug that more. You can also see that the total runtime is roughly the same time as it takes. So that means that everything happens under the context of the current thread. So that seems to be fine. So the thread rate statistics are also fine. There's not much delay on being scheduled, so probably not an overloaded system. And then also the soft IRQs are, not that much, 40 milliseconds, almost 50 milliseconds of RCU handling. So there's probably some heavy RCU stuff going on in the kernel. As you can see here, the other revalidator threads show similar behavior. The next step here would probably be to trace the individual send message syscalls to figure out why they take so long. The tool has an option for this. However, as mentioned earlier, the back traces do not show any useful information from a user space perspective. So I guess the next thing to do is to use a perf script for this. The tool's documentation has some nice example on how to do this. So this concludes the demo and the presentation. So are there any questions?
All right. So Let me check to see if there's any questions on my presentation. I guess everybody's trying to get ready for lunch here, or for dinner here in Europe, and probably lunch in the US. So let's see, no questions at the moment. Let's see here in the chat. All right, it's pretty quiet. So all right. Well, if there's no questions, then there's nothing for me to answer. So let's wrap it up for today. Oh, a new question just came in. It's pretty. Let's see what that question is. I just don't see it. Yes, let me open it. All right. So can this be used on the OVS DB server? Yes. So from an OVS perspective, sorry, from the trace tool perspective, it doesn't really care what the process is. It will do it for any process. Only when you start it up, it will automatically try to detect the PID of the OVS vSwitch D. So if you would override that with the PID on the command line of your OVS DB server, you should get exactly the same information. And if there is USDT probes or just any U probes that you would like to use, that should work just fine. I hope that answers your question. All right, I see another question from Flavio. Are there any new improvements planned for this tool? So at this moment, I have nothing on my list of things to add. But if there is anyone that has additional features that they think that that could be added, just let me know, and I'll try to work them in. So Aaron also asked, is there any other probes that we might to add to improve the tracing? I'm not really sure what you mean there, Aaron. Do you mean adding more probe types to the tool itself, or are you referring to adding more USDT probes within OVS? Maybe you can clarify that. All right, so more USDT probes, yes. So I think there is one outstanding patch that is there for a while, since last OVS conference, that adds some USDT probes for the revalidator, and I really would like to see that patch going in. I'll try to work on that patch myself, as the previous contributor does not seem to be active anymore. I pinged him a couple of weeks ago, so hopefully if he replies, I can take it over from him and continue that work. If there is any probe missing that anyone feels like they need, I think either submit a patch or get in touch with me, and we can work out maybe together what kind of a probe is required for your work. All right.